Good afternoon, everyone. Today, I'm going to give you a talk about Phrase2Vec in practice. I assume many of you already heard of Word2Vec. In BYOR, we not only use word vector, but we also use the phrase vector. And I am planning to do the exercise together with you on how to build phrase vectors using word vectors. The objective of this talk is to provide you with essentials on word vector and word embedding, because if you understand the word vector very well, then it is not too hard to combine them into phrase vector. I understand a lot of people at this conference just started their journey in NLP and machine learning, and I hope to give you some idea about word embedding and how to play with those vectors. Hi. Before we begin, I'd like to give you some brief introduction about BYOR, my startup. BYOR is Build Your Own Resume, and it's an AI-powered resume helper. When a user uploads her resume, it extracts the sentences and evaluates them and tells a user what she did well or what she can improve semantically on each sentence. It was a class project of Stanford online class CS2-4D by Dr. Richard Socher, Deep Learning in NLP. Then BYOR became popular, so I decided to do it full time. In terms of the format of the talk, I'll be able to answer a few questions while the talk, but if there are a lot of questions, I need to postpone answering them at the end of the talk. But if you need a few clarification, feel free to jump in. Let me share my screen. So at the end of this talk, we'll be able to calculate the similarity between two phrases by using word vectors. And you need to download these files on this link. And the file is the word embedding file that Google thankfully trained for us and made accessible to public. And the model contains 300 dimensional vectors for 3 million words. So you can think of this file as an output of what I'm going to describe in this talk. And you also need to install GenSim and NumPy, SciPy, and NLTK. So the question is, why did the word embedding become the most promising technology in NLP these days? Because it has been successful in solving many NLP tests, but also frustrations. Let's say we represent the word using binary vector. So we will represent every word as a vector with all zeros and only one here at the index of that word in the sorted English word. So this index, the index 0 will be like, let's say about, and this index will be account, and this index is apple. Then we put 1 here because this word is apple, and then all other index will have 0. And the fruit is the same. So only 1 and all zeros. So if there are 20,000 words in whole vocabulary, the vector size also will be 20,000. And there will be only 1 and 19,999 zeros in the vector. This representation is mainly used in rule-based model. And I am not being disrespectful to rule-based model, but is a very primitive way to represent the word. I call it primitive because it cannot capture the semantic relationship between apple and fruit. Because if we calculate the similarity by just dot producting these two vectors, like 0, 0, 0, 0, 1, 0. The similarity is just 0 if you do the end operation. And what about the dimensionality? It is very sparse representation, and the size of vector will be the number of vocabulary. So it's like 20K, 50K. So what's the solution? Solution is to use low dimensional vector, not the sparse high dimensional vector, but the dense and smaller vector. Our lofty goal in reducing the dimensionality is to store most of important information in the small number of dimension, like under 500. And if you have really large training data, maybe under 1,000. So how can we do it? How can we do that? We're going to build co-occurrence matrix, and then we will use SVD, singular value decomposition, to reduce the dimension. And I will show you one very simple and very arbitrary example. Let me share a different screen. So there are 3 corpus. Donald Trump has many buildings, period. Can you guys see the screen? Okay. And Mr. Trump owns many factories in China, period. Donald Trump has relatively small hands, period. And we have those words. And we are building 14 by 14 array because the number of words here is 14. And we are only using NumPy and PyPlot and linear algebra. And what I'm doing here is just counting the co-occurrence. And we are applying SVD here and plot the first 2 orthonormal columns. So let's run this. Paste magic. And here, the word got plotted. Trump has Donald owns Mr. And this part is interesting. Buildings and factories appeared very close together. And if I show you the co-occurrence matrix, it looks like this, and it's in the slide as well. So if you see this co-occurrence vector, buildings and factories, even though we didn't even apply singular value decomposition, is pretty similar. Building has 1 and 1 at the same index, and has factor and owns factor has also 2, 1, 1, 1. You can say it's pretty similar. So it's just like three sentences matrix. And the reason why I'm showing you this co-occurrence table in this depth is because I was wondering, is analogy a unique property of word embedding? Is there something specific or something magical in the neural network that causes this analogical properties to emerge? But then the answer is no. They can be also found using this traditional sparse representation, as you see. It's similar. But the problem of this method is this SVD has its own weakness because its computational cost is quadratic. So it is not good for millions of words. And second, every time the word is added, we have to update the whole matrix. For example, if we add Melania Trump is a beautiful model, then we have to do the counting all over again. So we have to find the better solution. Oh, and here, the reason why I put the space between buildings and period and China period and Hansen period is because when we parse this phrase, we are using this line 26 split method. And if we don't put the space between this period and buildings period becomes its own token. But I wanted to buildings as its own token and the period as its own token. You can train it without split like this, but then you will have two different tokens, buildings period as a one token and buildings as another token. I just wanted to explain this to you. Okay. So what's the better solution? Better solution is, instead of capturing these core current counts directly, we're going to predict surrounding words of every word. So given the center word, like here, can I predict the word to the right or words to the left? Like given the word presidency, can I predict the Trump on the right or on the left? The question that I just asked is the main concept of Word2Vec. And Word2Vec is also a statistical NLP method. And if I have to summarize Word2Vec in one sentence, is you shall be judged by the company that you keep. So this is one of the most successful widespread idea of statistical NLP. And it's also the basis of Word2Vec. And traditional NLP uses this idea as well. But then, what's the hype? It's again capturing the co-occurrence matrix, just like the previous method. The thing is, Word2Vec is doing this in a very easy, streamlined way. Adding new words and updating new words is much easier because you will have a window. You don't have to update the whole 25 million by 25 million matrix every time. So I'll show you that in next slide. And I also want to give you some tips about the function words like for, and of, the. There can be many different ways to handle this. You can set the co-occurrence count as 0, but a little better solution for that is to set it as the minimum number in that column, or you can set the ceiling. There's no silver bullet that will always work the best. You should try different methods and test them to see which one performs the best on your end application. And here's the objective function of Word2Vec. Here's a theta, here's a big T, small t, and M, and log probability. And here the theta is all word vectors, all variables that we are going to jointly optimize while we are reading the corpus. And this big T is number of token. If you have a very large corpus, it can be billions. It will take very long time to train. But and this big T is not the distinct number of the number of distinct words. It's the number of every word used in that corpus. And M is the length of window to predict M words to the left and M words to the right. And here, this is log probability of context word. This is context word, and WT is the center word. So context word given the word in the center. Here, the probability of Trump given the word presidency. So, and the goal is to maximize the log probability of any context word given the current center word. I inserted this slide just to help you understand the vector better, the big, very big vector theta, because it is not always easy to visualize the vector. And if you look at here, zebra vector appeared twice, V zebra and U zebra. It's because every word has two vectors. U is the context word and V is the center word. And we are doing it this way to make the computation easy, because here the presidency used to be a center word, and then if the window moves to the right, it becomes the context word. So you might wonder which vector to use at the end. And my answer is you can either average them or concatenate them. It might not be the most beautiful way to treat the vectors, but it works very well that way. And each V and U are n-dimensional vectors. So it's very big vector theta has the inside, it has small vectors, not small, it's like 300 to 500 dimension vectors inside. So this will be very high dimensional vector, because the number of words will be more than 1,000, 100,000s, and then it has like, let's say 300 dimensions in every index. So to minimize the objective function j theta with respect to this gigantic vector, we have to compute gradients for all windows. And the number of tokens in corpus is 100 millions, and there will be another 100 millions of windows. So it's just not scalable at all. And this normalization part, the denominator, is also very expensive to calculate. So what should we do? How can we approximate this normalization constant? It's a hack. We're going to define the negative predictions. That means you only sample some words that do not appear within the context. Because if you have millions of words, most of words do not appear together. For example, the word calculator would rarely appear with the word amphibian. The word amphibian doesn't give that much information about word calculator either. So negative sampling is one of the ways to address this problem. Just by selecting a couple of context words at random, we can avoid this huge computation. So for any given word, you have a list of words that need to be similar to it, which is called positive class, and the words which are not similar to the target words, which is called negative class. And they are compiled by sampling. So let's look at the equation. Trump announced his candidacy for president as a Republican. And we will take the exponential of U transpose V. And the reason why we take the exponential is so that we can have positive number in the numerator, because it's probability. And the idea of Word2Vec is to maximize similarity between vectors which appear close together in the text and minimize the similarity of words that do not appear together. And we measure the similarity using the dot product. And after we optimize the word candidacy, we'll move to the for and then president and as a Republican. And we are moving one word at a time, and try to maximize the probability. So what do we get after this huge optimization? We get the word vectors, word vector that encaptured the semantic and syntactic properties of training corpus. And here is the famous example. King vector minus man vector is similar to the vector direction of queen vector minus woman vector. So maybe that vector is royalty vector. And because BYOR uses lots of software engineering related corpus, CSS minus front end, we can see that Django minus backend. They are pretty similar vector as well. And besides the semantic information, which is a very interesting result, also syntactic information is captured. Singular, plural is captured, and also the tense is captured. And what's captured in this co-occurrence statistics is fascinating. All those information is in this vector space, even though we didn't provide any information about information about their semantics. But don't fall into the misconception like, oh, machine like knows everything, understands everything. It's not really. It's just co-occurrence statistics. We trained it with the right corpus. And we trained Wikipedia pages related to software engineering. Then we applied SVD and print out the first two columns of vector corresponding to the two biggest singular values. So as you see, keywords in the same categories naturally appear together. So correlation, regression, logistics, Bayesian, they are statistics keyword. And MapReduce, they are own kind MapReduce. And CSS3, HTML, Ajax, they are front-end related keywords. And Hadoop file system, MySQL, SQL, NoSQL, they are database keywords. And classifying job-related keywords into right categories is important in resume reviewing. And previously, only people with technical backgrounds were able to tell these differences between tech keywords, and only they were able to classify them into right meta groups. But we automated this classification using word embedding. And of course, the vectors can be used with any conventional clustering algorithms, such as k-means or hierarchical, etc. Another example of how we use the vectors, you can see that the words on either side of three somewhat parallel vectors share similar relationships to each other. K-means, SVM, ANOVA, they are the methodologies of clustering, classification, and statistics. So more sophisticated relationships are encoded in this way. Okay, so exercise time. Please go to this link and download the repository. And Gilami, the size of window for neighboring words can be tuned. Yes, it can be tuned. It's not always +1, -1. And what else? Okay, I assume you guys downloaded the repository and the vector file, and I'll keep explaining the code. In the repository, there will be a file called with the best WTB phrase similarity.py, and create the data folder there and put the Google vectors -300.binary file into that data folder. And we are going to use Gensim's Word2Vec class to read that pre-trained vector. And this and we save it in the variable called model1, and this model1 becomes our dictionary. So it works like this. So model1, if you want to look for resume vector, then type resume. And this is how resume vector look like. And if you want to look up the word vector for banana, this is word vector for banana. And we are not going to use too many fancy modules, but then we will use NumPy and Math and SciPy and NLTK. And this is phrase vectors. We are going to make the phrase vector by averaging the word vectors in the phrase. And there are other ways to make phrase vectors, such as you can first train the TensorFlow to do the machine translation and then retrieve the hidden state. And again, Word2Vec is unsupervised learning, so there is no one good way to objectively evaluate the result. The evaluation will depend on your end applications. So you won't know until the phrase vector would work, which phrase vector would work better on your application, until you try and come up with your own test. So here, we take the user input as a raw input and save it into user input 1 and 2, and we call the phrase vector class. Then all it does is just split the phrase the user entered and look up the word in the model dictionary, and we take the average. And the average, like taking average of vectors, is really easy, just NumPy mean and vector set. And then we calculate the cosine similarity, and that method is declared here. And it's just, we're using NumPy dot and NumPy norm and linear algebra norm. And let's try this. So type the phrase 1. How Trump would simulate the US economy is our phrase 1. And phrase 2 will be Trump unveils plan to revitalize Americans' economy. And the similarity score is 73%. So it's pretty similar. And another phrase 1, let's make America great again. And phrase 2, we'll make America prosperous and powerful, 67% similar. And let's make America great again. And we are going to build a beautiful wall. It's 43% similar. Based on my experience, if the similarity score is greater than 60%, you can assume that those two phrases have similar meaning. And if it's less than 50%, you can assume that it's not that similar. Okay, I think I need to wrap up this talk. So you can go to, yes, it's 3.6 gigabyte file. So you probably need at least 10 minutes to download. If you have, so the code is out there on Bitbucket, so feel free to download. And if you have questions, just drop me an email. It's BYOR@BYOR.xyz. And please check out our website as well. It's BYOR.xyz. And so tested our AI technology, and we are featured on Product Hunt. So please upvote us if you like our product. And thank you for attending this talk. I had a fun. Thanks. Bye.